I would like to start this presentation with a couple of questions. The first would be if we can design for sustainability, paying attention only to the economic costs along the life cycle of our structures, or if it is maybe necessary to include environmental aspects as well. Another question would be how should we do this effectively? This communication will show that sustainability must be assessed taking into account not only economy and environment, but also social aspects. Along this presentation, we will pay special attention to how sustainable criteria will influence on both the design to be chosen for a particular bridge and on the optimal maintenance intervals that lead to the best sustainability response. This is the overview of this presentation. We will first go through a short introduction, then we will talk about the research methodology. After that, I will present the results obtained from this study, and at last, we will describe the most relevant conclusions from this analysis, from this study. Finally, some references will be provided for those of you that might be interested in reading more about this topic. So, in recent times, the construction sector has become a major source of impacts on both the global economy, the environment, and the society. The recently established Sustainable Development Goals therefore acknowledge that the design of sustainable infrastructure is essential to achieve the sustainable future to which we all aspire. From a life cycle perspective, it is the maintenance phase of an infrastructure that has been recognized as a main contributor to its resulting life cycle impacts. In coastal regions, concrete structures are exposed to really aggressive environments that demand a significant number of maintenance activities along their life cycle, so as to guarantee adequate serviceability levels. Optimization of maintenance in such environments and for such structures is therefore essential when aiming to a sustainable future. As sustainability assessments rely on conflicting criteria, the terms in which such optimality shall be defined have become a matter of discussion over the past years. This communication aims to analyze how the optimization of maintenance activities in aggressive environments may lead to different design strategies depending on the perspective that is assessed, namely the economic, the environmental, or the social perspective. It will be also analyzed the optimization results that are obtained after a simultaneous consideration of all the three sustainability dimensions. The sustainability assessment held here will be based on the ISO 14 series standards, which establish the 4 steps to be followed for conducting environmental life cycle assessments. The first step, according to those standards, is to define clearly the problem to be assessed, which is called goal and scope, according to the ISO series. So, this study focuses on 7 alternative designs for a particular prestressed concrete bridge deck located in Galicia, in Spain. It consists of a 12-meter wide box girder deck with a total deck depth of 2.5 meters. The concrete cover is assumed to be 40 millimeters, and also a passive reinforcement amount of 100 kilos per cubic meter is assumed here in this study. The alternatives considered base their durability on different resisting mechanisms against chloride ingress and chloride-induced corrosion, such as reduced porosity of the concrete cover, increased resistance of reinforcement steel against corrosion, the use of increased concrete covers, or the generation of a surface barrier that prevents the chloride ingress. All of that is materialized in the 7 alternatives that are listed here in this slide. As a first alternative, the water-to-cement ratio of the baseline concrete mix will be reduced to 0.35. Also, particular materials will be added to the baseline mix. These alternatives consist of adding 5% silica fume, 10% fly ash, or 10% latex. A design alternative considering galvanized steel reinforcement will be also analyzed. And at last, the performance of hydrophobic surface treatments applied to the deck surface will also be evaluated. The table in the right shows the concrete mixes assumed for each of those 7 alternatives. The functional unit of the present analysis consists of a 1 meter long section of the mentioned bridge deck, including all the construction and maintenance works required to guarantee a service life of 100 years, according to national standards. For the analysis, a gate-to-grave approach has been followed. That means that all the impacts related to the extraction of raw materials and production of the different construction materials that are needed for both the construction and for the maintenance operations will be considered explicitly. This analysis also takes into account the impacts associated to the transport activities between the different production centers and also between the production centers and the installation site, as well as those related to electricity and diesel required by the machinery involved in the different activities. The assessment of the economic life cycle impacts will take into account 2 different impact categories, namely construction and maintenance costs. Here, a so-called social discount rate of 2% will be chosen in order to discount future costs. Environmental impacts will be assessed based on the Recipe 2008 methodology. This methodology allows for the conversion of the inventory data characterizing the system under analysis, such as energy or materials consumption rates, into quantifiable impacts, which will be expressed as 18 different midpoint indicators. One of the advantages of this methodology is that in the end, those 18 midpoint indicators can be translated into 3 endpoint indicators that are more comprehensive, which are damage to ecosystems, availability of resources, and damage to human health. At last, the social impacts will be assessed following the indicator-based impact methodology proposed by Navarro et al. This methodology considers 4 main social impact categories for bridges in Spain, namely the impacts related to workers and employment generation, the impacts on the economic development of the regions affected by the activities associated to construction and maintenance, the impacts on the bridge deck users, and the impacts on the public opinion and the aesthetics of the bridge site. Finally, sustainability will be assessed taking into account the mentioned 9 impact categories. As these criteria are conflicting, a multi-criteria decision-making technique will be used, in this case, a TOPSIS technique. First, the relevance of each criterion is determined by using the analytic hierarchy process, or AHP. Once the relevances are assigned to each criterion, TOPSIS is then used to find the design alternative and the particular maintenance interval that maximizes the resulting life cycle sustainability performance. The data for the environmental characterization of each material and process has been gathered from the database EcoInvent 3.2 and complemented also with process performances shown in the first table here. The economic data has been gathered from national construction-specific databases, and at last, the social data can be obtained from in this case, from the Spanish Tax Office and the Spanish National Statistics Institute. So as to establish the maintenance needs for each of the design options under study, a deterioration model shall be chosen. In coastal regions, the main deterioration mechanism affecting concrete structures is usually the chloride corrosion. So to evaluate the advance of the chloride front in concrete over time, a two-dimensional version of the Fickian model proposed in FIB Bulletin 34 will be used. The particular values for the durability parameters of each design alternative are given in the table shown there to the right. On the basis of these values, the failure probability at any time can be evaluated by means of Monte Carlo simulations. In this case, considering that failure will occur when the chloride concentration exceeds the critical chloride content at the river depth. Maintenance is considered here to be mandatory at the time when the reliability reaches a level of 1.3, which corresponds to a 10% failure probability. Such limit maintenance interval corresponds to our reactive maintenance strategy. So maintenance will be optimized by finding those intervals below these reactive intervals that maximize the life cycle sustainability performance of the alternatives. So let us go straight forward to the results obtained. So firstly, considering costs, the alternative that performs best is the design based on the periodical reapplication of hydrophobic surface treatment, followed by the alternative with silica fume. The good results, in economic terms, of those options rely on the significantly reduced maintenance costs. In the case of hydro, these costs are almost negligible, as we can see in the figure here. As for this design, the concrete cover must not be replaced in maintenance activities. On the contrary, the alternative based on the use of silica fume bases the reduced maintenance costs on the high durability of the solution, which can last up to 35 years without any need of maintenance. From the results shown here, it shall be also observed that the optimum maintenance for these two well-performing solutions is based on a reactive strategy. For the other design options, it is preventive maintenance, the one that leads to reduced life cycle costs, leading in some cases to reductions of maintenance costs up to 14% if compared to their corresponding reactive maintenance results. When it comes to environment, the most relevant impacts can be seen that are those affecting the human health and the depletion of natural resources. In particular, it is the availability of resources what takes the greatest proportion of the total impact, taking up to almost 60% of the total life cycle impact in some cases. In general, it is observed that the lesser maintenance required, the lower the resulting impacts to the environment. However, the alternative based on the application of hydrophobic surface treatments every 5 years has proven to lead to the best results despite the high maintenance needs. This is because for this alternative, the environmental impacts associated to the production of concrete for each maintenance operation are avoided due to the fact that the concrete cover shall not be replaced every time. Preventive maintenance has shown in this case that reductions in the environmental impacts of up to 16% can be achieved if compared with the reactive strategies. From a social point of view, the best option is the one based on the use of silica foam additions, which is the design with the greatest durability. According to the assessment methodology proposed by NAVARRO et al., the positive impact on the stakeholders, consumer, and local community will be greater the lesser maintenance is required. It is observed that in the case of silica fume additions, the impact on these two stakeholders in particular takes more than the half of the total social life cycle impacts. Consequently, it is straightforward that maintenance demanding alternatives such as hydro or also those with reduced durability result in the worst social performance. In those cases, the positive impacts on consumers and also on the public opinion of the local community are almost negligible in comparison with impacts on workers and on the economic development of regions. Regarding the contribution to the workers and to the economy of the regions involved along the value chain of the bridge, it is observed that those alternatives that are based on construction materials that require technically demanding production processes, such as the production of galvanized steel or the production of latex, result in the greatest impacts on these two stakeholders. At last, to assess the sustainability of the designs under analysis, a panel of experts have been consulted so as to determine the relevance to be provided to each criterion in the evaluation. The resulting relevance of each criterion is given in the table shown here. The solution that performs best from the point of view of sustainability is the design based on the use of silica fume. On the contrary, the worst performing solution is the one based on the addition of latex to the baseline concrete mix. It is interesting to note that the solution based on silica fume additions was not the best solution in neither the economic nor in the environmental assessments. So at last, to conclude this analysis, this study, it can be observed that each of the approaches presented here has resulted in different optimal maintenance intervals and different life cycle performance values. It has been observed as well that those differences are greater for alternatives with reduced durability. It has to be said as well that no significant relationship has been found between the obtained results in each of the assessments considered separately and with the holistic sustainability approach. So it follows that designing for sustainability requires of the simultaneous consideration of each of its three dimensions. So the present communication has shown the discrepancies that can be expected when designing bridge structures in aggressive environments from different life cycle perspectives. Those discrepancies are materialized both in the selection of construction materials and in the selection of the optimal maintenance as well. So from the obtained results, it is concluded, or it can be concluded, that sustainability-oriented designs shall not be based on the sole consideration of only one of the three dimensions of sustainability when talking about life cycle assessments. This paper has shown that sustainability shall only be addressed from a three-dimensional or holistic perspective, taking simultaneously into account the economic, the environmental, and the social consequences of every life cycle activity associated to the structure to be designed. At last, here you will find some of the references of the research group that can be consulted for those of you that are willing to investigate further on the sustainability assessment of structures. Thank you very much for your attention.